Hey there, everyone. Welcome to Chapter 12. So, as you hopefully have seen already, Chapter 12 is all about static equilibrium, right? Static meaning stationary, right? Or no movement. Nothing is moving. In other words, nothing is accelerating through space. And that means nothing has a linear acceleration. So the sigma f equations are all equal to zero, and nothing has an angular acceleration. So the sigma tau equations for the net torque will be equal to zero. All right. We'll still need to do all of the free body diagram analyses, right, for forces and torques. But since nothing's moving, nothing's accelerating, all of those equations will be equal to zero. So I wanted to start off somewhat simply with this example here. It's just a mass hanging from some central point connected by two strings. This wouldn't have any rotation to it, right? If you could imagine one of these strings being cut, say severed there or severed there, what would happen? Well, this ball would fall straight down, right? It would accelerate straight down. It wouldn't necessarily rotate. And these are strings, not like rigid poles or rigid rods. Okay? So this is a problem with just forces at play. We won't deal with torques in this example. So what we have here is that mass hanging from some central point, and that central point also has connected to it two strings, right, under some tension. And so we'll call string from point B to C, we'll call that string 1, right? And we'll call the string from point B to A string 2, okay? And I'm only doing it 1 and 2 because the angles in the image are already labeled 1 and 2, okay? So that means from this central point, there will be some tension, right, on that knot or on that point, right? That tension for this string, for string 1, we'll be pulling it that direction. And by it, I mean, well, this string and the mass, right? Conversely, string 2 will have a tension this direction, trying to pull string 1 and mass, in that direction. And then the mass itself is subject to gravity, so its weight has a force downwards, okay, straight downwards. So let's draw a free body diagram for this situation. So let's start at the central point right there, right? That connects all three strings or all three objects in this problem. Okay, I want to break up both tensions into their x and y components, right? So tell you what, let's do string 1 first, right? Theta 1 is designated right here, right? It's touching, say, the horizontal part. So that means we can do the x1 first. That means this will be T1 cosine of theta 1, right? And I haven't put any signs in this part, right? That means also the y direction will be T1 sine of theta 1. Again, because it's the opposite component to the angle, okay? I just have transposed it coming from the central point. For string 2, that has a tension to the right of T2 cosine theta 2. And actually, the y component, right, the sine component for tension 2 is downwards, like that. So I'm going to draw that coming from the center. And this can be written as T2 sine theta 2. All right? And so those are all four of those tensions for strings 1 and 2. Now we just have the ball, right? So if you think about it, if we zoom in, let's try this here. If we zoom in right there on that string, will this work? Oh, no, it won't. from that central knot, we have really a tension downwards, right? And a tension upwards, right? All because of the particle's gravitational pull, right? It has a weight, mg downwards. And so really, that causes two equal and opposite tensions in that intermediate string, right? But they cancel out really, and so the external force to this system, with the system being, where is it? The system being string 1, string 2, and this mass, right? All of this as the system. The external force comes from gravity. And so that's why we need this force in our free body diagram, like so, okay? We don't necessarily need to write, those forces there. Okay, so now we have all 5 forces at play, okay, acting on that central knot. So it's time, like usual, to write up the net force equations, right? The second law equations. So sum of the forces in the x direction. Well, we haven't designated the x direction, so let's do that now. So if I choose right to be positive, we have T2 cosine theta 2, that's it, minus, or that's it for the positive ones rather, minus T1 cosine theta 1. That's all for the x components, and so there's no acceleration, so it's equal to 0. The y direction, positive, we have the T1 sine theta 1 minus T2 sine theta 2 minus the weight, and that's also equal to 0. Excuse me. All right, so now we need to find the tensions in both strings, right? BC actually is tension, I said that was 1, this is tension 2. Okay, well, we have 2 equations and 2 unknowns, right? The mass is given to us, the angles are given to us, and we know g, but that's a constant. So I'm going to solve one of these equations for one of the tensions and plug that expression into the other equation, okay? So I'm going to solve the x equation, for T1, okay? So solving the x equation for T1 gives us something like this. Right? Put both terms on either side, and then solving for T1 gives us an expression of this, right? And now this is what I'm going to plug in. All that, I'm going to plug it in right there. Okay? So what we have now is parentheses T2 cosine theta 2 over cosine theta 1 times sine of theta 1 minus T2 sine theta 2, and I'm going to go ahead and solve for mg, right? Put that on the right side, right? And now we have one equation and one unknown, and that's tension 2, right? T2. So if you rearrange for those and plug in the values, tension for string 2 should give you 15.3 or 26 newtons. Okay? So that should be your answer for one of them. And then you would take this value right here and plug it into either this equation or that equation. It doesn't matter. You'll get the same answer. And then solve for T1. Okay? If you do, T1 should give you an answer of 28.7 newtons. All right? So, to reason this a little bit, right? All this stuff here was just math, right? again, this was the physics part. This was the important part. And now, to sum up and see if our answers make a little sense, T1, that was a little bit more vertical, right, than T2 is. So the magnitude of T1 should be larger than T2, and it is, right? Really, the tension will be a maximum magnitude if it's exactly vertical. That means it's exactly equal to the object's weight. So the closer to that, the vertical direction, the closer to that up, right, the larger it should be. And that holds true here. Okay? So that should match intuition, but this is, in general, how we do these problems. It's very similar to back in chapter 5, right? Or back in chapter 6 even. We didn't have friction here, and we didn't have acceleration, but the free body diagram is the same. Okay? With that, thanks for watching.